Feynman's Nobel Prize idea. Antimatter doesn't exist. It's time. In 1949, Richard Feynman shared the Nobel Prize in Physics for work that sounds almost impossible to believe. He proposed that antimatter isn't really a separate thing at all, that it might be ordinary matter, traveling backward through time. Not in some poetic sense, not as a metaphor, but as a legitimate mathematical description of what's actually happening in the universe. And the strangest part? The math works perfectly. Experimentalists use this interpretation every single day. It's woven into the foundations of modern physics. But here's what makes this genuinely unsettling. When we say traveling backward in time, we don't mean what you probably think we mean. This isn't about paradoxes or changing the past. This is about something much more fundamental. Something that forces us to reconsider what we even mean when we use the word time. Tonight, I want to walk you through this idea carefully, because it's one of the most elegant and counterintuitive concepts in all of physics, and it starts with a problem that nobody knew how to solve. The crisis in the equations. In 1928, Paul Dirac was trying to write down a proper quantum mechanical equation for the electron. This sounds technical, but the goal was simple. Physicists had quantum mechanics. They had special relativity. Dirac wanted to merge them into one consistent mathematical framework. He succeeded. The equation he wrote down is now called the Dirac equation. It describes electrons moving at any speed, including speeds close to light. It predicted electron spin before anyone had properly understood spin. It was brilliant. But there was a catastrophic problem buried inside it. The equation had two sets of solutions. One set described electrons with positive energy, which made perfect sense, but the other set described electrons with negative energy, and nobody knew what that meant. Negative energy doesn't show up in everyday experience. You don't encounter objects with less than zero energy sitting around in the world. Energy levels in normal physics have a lower bound. You can't go below the ground state. But in Dirac's equation, there was no floor. An electron could have arbitrarily negative energy, infinitely negative even. This created an immediate crisis. If electrons could drop into these negative energy states, then all of matter would be unstable. Every atom in your body should radiate energy and collapse into these bottomless states. The universe should have destroyed itself instantly. Obviously, that hadn't happened. So something was deeply wrong, either with the equation or with the interpretation. Dirac tried to patch the problem. He proposed that maybe all the negative energy states were already filled, completely occupied by an invisible sea of negative energy electrons. Real electrons couldn't fall into them because there was no room left. It was creative, but it felt contrived. And it didn't explain what would happen if one of those negative energy electrons got kicked out of the sea. You'd have a hole, a missing negative charge, which would look like a positive charge. Dirac predicted that such a hole would behave like a positively charged electron. And in 1932, Carl Anderson found exactly that. He called it the positron, the first piece of antimatter ever discovered. So the math was right. The equation worked. But the explanation still felt uncomfortable. Why would nature bother with this elaborate structure? Why have a sea of invisible particles just to avoid a mathematical problem? Physicists used the theory because it worked. But many of them suspected there had to be a better way to understand what was really going on. The student and the phone call. Richard Feynman was a graduate student at Princeton in the late 1930s when his advisor John Wheeler called him with an unusual idea. Wheeler had been thinking about the infinite sea problem, and he wondered, what if we don't need the sea at all? What if a positron isn't a hole in anything? What if it's just an ordinary electron, but moving backward in time? Feynman thought this sounded crazy, but Wheeler insisted they work through the mathematics together. And when they did, something remarkable happened. If you take an electron and reverse its direction in time, The math says it behaves exactly like a positron. Same mass, same spin, opposite charge, opposite energy flow. Not similar, identical. Here's the key insight. In physics equations, time appears as a variable. We usually call it t. When you describe a particle moving forward in time, t increases. The particle goes from earlier moments to later ones. But mathematically, there's nothing stopping you from putting a negative sign in front of t. If you do that, the particle's time coordinate runs backward. Earlier to later becomes later to earlier. When you apply this time reversal to an electron in the Dirac equation, all of its properties flip in exactly the right way to match what we observe for a positron. The negative energy solution disappears. You don't need an infinite C. You just need to reinterpret the mathematics. A positron isn't a fundamentally different particle. It's an electron, moving along its world line in reverse. What this actually means now, we need to be extremely careful here. When physicists say moving backward in time, they do not mean the particle is experiencing time in reverse. They do not mean it's remembering the future or that causality is broken. This is a description of the particle's mathematical trajectory through space-time, not a description of subjective experience or consciousness. Particles don't have experiences. Think about space-time as a four-dimensional structure. 3 dimensions of space, 1 of time. A particle's path through this structure is called a world line. Most particles have world lines that tilt forward in time. As they move through space, they also move from past to future. But mathematically, nothing in the fundamental equations demands that this tilt always goes the same direction. If you have a world line that tilts backward in time, the particle appears to move from future to past. And when you calculate what properties such a particle would have, you get exactly the properties of antimatter. The charge flips because electric charge is coupled to the direction of motion through time. Reverse one, reverse the other. The energy flips from negative to positive because you're now counting it in the opposite temporal direction. What looked like an electron losing energy going forward looks like a positron gaining energy going backward. This isn't a trick. It's not a mathematical game. It's a genuine equivalence. The two descriptions produce identical predictions for every experiment we can perform. Feynman diagrams and the visualization. Feynman developed a visual language to make this easier to work with. We call them Feynman diagrams, and they've become one of the most important tools in particle physics. In these diagrams, time usually runs upward or to the right. Particles are represented as lines. Interactions happen where lines meet. An electron moving forward in time is drawn as a line with an arrow pointing in the direction time flows. A positron moving forward in time is drawn as a line with an arrow pointing backward against the time direction. Why? Because that's what it is in this interpretation. An electron whose world line runs counter to the time axis. Here's where it gets visually striking. When an electron and positron annihilate, the diagram shows something unexpected. You have an electron line moving forward in time. Then at a certain point, the line reverses direction. It starts moving backward in time, and we now call it a positron. From an external perspective, it looks like the electron and positron came together and disappeared. But from the particle's perspective, if we can even use that phrase, it's a single electron, changing direction in time. Imagine watching a recording of someone walking across a room. Then you rewind the tape. On the screen, it looks like a different person walking backward. But it's the same person, same recording, just played in reverse. In Feynman's interpretation, annihilation isn't destruction. It's a U-turn in time. And pair production, where a photon spontaneously creates an electron-positron pair, is the same electron making that U-turn. One electron folding its world line back on itself. Wheeler even joked once that maybe there's only one electron in the entire universe, zigzagging back and forth through time, creating the appearance of countless particles. Feynman knew that was too simple, but the image captures the idea. What we interpret as many particles moving forward might be fewer particles, moving in more complicated ways through time. What this does not mean. Let's address the obvious questions. Does this mean we can build a time machine? No. Does this mean antimatter can be used to send information to the past? No. Does this mean causality is violated? No. Here's why. Individual quantum particles do not experience entropy. They are reversible. Their behavior at the microscopic level is symmetric in time. The equations that govern a single electron don't distinguish past from future. But macroscopic objects, including us, are made of enormous numbers of particles. And at that scale, entropy dominates everything. Entropy is the measure of disorder, and the second law of thermodynamics says it always increases. This isn't a fundamental law in the same way gravity is. It's a statistical inevitability. There are vastly more disordered states than ordered ones, so systems naturally drift toward disorder. This gives time an arrow, a direction. The past is the direction of lower entropy. The future is the direction of higher entropy. Even if individual particles can have world lines that fold backward, those micro-reverses don't propagate to the macroscopic scale. You can't steer them. You can't use them to send messages or preserve memories backward through time. When an electron reverses its time direction, it doesn't carry information about the future back to the past. It's simply following the allowed mathematics of quantum field theory. So the time symmetry that exists at the particle level does not give us time travel. It gives us a more accurate description of what particles are and how they interact. Time symmetry in the equations. There's something deeper here worth sitting with. The fundamental equations of physics at the quantum level do not have a built-in arrow of time. If you take any process allowed by these equations and run it backward, you get another allowed process. An electron emitting a photon can run in reverse as a photon being absorbed. A particle decay can run in reverse as particles fusing. The equations don't prefer one direction over the other. This is called time reversal symmetry, or T-symmetry. And for a long time, physicists thought it was absolute. We now know there are extremely rare processes involving certain particles, like kaons, that do violate T-symmetry. But these violations are tiny. They don't affect the overall picture we're discussing tonight. For the vast majority of physics, time is symmetric. The equations work just as well forward or backward. And yet, we experience time as deeply asymmetric. We remember the past, not the future. We see eggs break, never unbreak. We age in one direction. This asymmetry doesn't come from the fundamental laws. It comes from the initial conditions of the universe. The Big Bang started everything in an extremely low entropy state, and ever since entropy has been increasing. That increase is what gives time its felt direction. But underneath, at the level of individual particles, there is no arrow. There is only the mathematics. And the mathematics allows world lines to tilt in either temporal direction. Feynman's interpretation takes that symmetry seriously. If the equations treat forward and backward as equivalent, then maybe we should too. Maybe antimatter isn't a separate category of stuff. Maybe it's just matter, described from the other side of the time-symmetric coin. The modern perspective. You might think this interpretation is outdated, something physicists believed in the 1940s but have since moved past. That's not true. Feynman's time-reversed interpretation of antimatter is still taught in every graduate-level quantum field theory course. It's still used in calculations. It's still the cleanest way to understand many particle interactions. Modern quantum field theory describes particles as excitations in underlying fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Antimatter, in this framework, corresponds to excitations that have opposite quantum numbers, opposite charge, opposite lepton number, and mathematically, these opposite quantum numbers arise naturally if you describe the excitation as moving in the opposite time direction. It's not that physicists sit around debating whether positrons are really moving backward in time. The question isn't framed that way anymore. Instead, the question is, what's the most useful mathematical description? And time reversal remains one of the most useful. Feynman diagrams are still the lingua franca of particle physics. Every interaction, every scattering event, every decay process is sketched out using these diagrams. And in those diagrams, antimatter lines run counter to the time axis. Experimentalists at the Large Hadron Collider use Feynman diagrams to predict what they should see when protons smash together. The diagrams tell them which particles will be produced, at what rates, with what energies. And those diagrams are built on the idea that antimatter can be represented as matter moving backward. It works. It keeps working. And that's what matters in physics. The elegance of the idea. There's something beautiful about this way of thinking. It takes a problem, negative energy solutions, and instead of adding new assumptions, it reinterprets what we already have. You don't need an infinite sea of particles. You don't need a separate creation mechanism for antimatter. You just need to take time symmetry seriously. And when you do, antimatter emerges naturally. It's not an extra feature of the universe. It's a consequence of the symmetry that was already there. This kind of elegance is rare in physics. Most of the time, explaining something new requires adding complexity. New fields, new particles, new interactions. But occasionally, you find an idea that simplifies, that reveals hidden structure in what you already understood. Feynman's interpretation of antimatter is one of those ideas. It doesn't add to the theory. It clarifies it. It shows that the distinction between matter and antimatter isn't as fundamental as it seems. It's a question of perspective, of which direction you're tracing the world line. And that's a profound shift. It suggests that some of the categories we use to carve up reality are more flexible than we thought. What we're left with. So where does this leave us? Antimatter is real. Positrons exist. You can create them in a lab. You can trap them. You can study their properties. But what they are, at the deepest level, might not be what we intuitively assume. They might not be a different kind of particle. They might be the same particles, moving through space-time in a way that looks reversed to us. This doesn't make antimatter less real. It makes it more interesting. It tells us that time, at the quantum level, is not the simple forward-flowing thing we experience in daily life. It tells us that the universe doesn't care about past and future the way we do. Those concepts are useful for creatures like us, who live in a macroscopic world dominated by entropy. But they aren't written into the bedrock of physics. And it tells us that some of the most profound ideas in science come not from discovering new things, but from reinterpreting what we already know. Feynman didn't discover antimatter. Carl Anderson did that. What Feynman discovered was a new way to think about it, a way that stripped away unnecessary assumptions and revealed the symmetry underneath. And that way of thinking has lasted. It's still here, 80 years later, still guiding how physicists understand the quantum world. Closing. If you've made it this far, you've just spent 20 minutes thinking about one of the strangest ideas in modern physics. And maybe you're sitting there wondering, is this really true? Is antimatter actually moving backward in time? The honest answer is that the question isn't quite right. Physics doesn't tell us what's really happening in some ultimate metaphysical sense. It tells us which mathematical descriptions work, which models make accurate predictions, which frameworks let us calculate what we'll observe. And the time-reversed description of antimatter works. It's not the only description. You can formulate quantum field theory without ever mentioning time reversal. But it's one of the most elegant, one of the most powerful, one of the most widely used. So maybe the better question is, why does the universe allow this description to work? Why is time symmetry so deeply embedded in the laws of physics? Why do the equations not care which direction we call forward? Nobody knows. But the fact that we can even ask these questions, the fact that we've built mathematical tools precise enough to describe particles moving backward through time, is itself extraordinary. We live in a universe where the mathematics of nature is stranger and more beautiful than anything we could have invented. And every so often, someone like Feynman comes along and shows us just how strange it really is. Thanks for watching.